All right, next we're going to look at a couple of geometric applications of ellipses. So what I'm going to do is I'm going to draw an ellipse by hand. Of course, it's not going to be perfect. I don't expect yours to be perfect either. Now, we remember the definition of an ellipse being the set of all points such that if we have two foci, the plural of focus, if we look at any point on the ellipse, the sum of the distances from that point to the two foci ends up being constant. So the sum of these two distances equals the sum of these two distances. That was the definition, geometrically, of an ellipse, but there's also a reflective property. If we have light waves or sound waves or other signals coming from one focus, when they're emanated out and they reflect off the edge of the ellipse, they all get reflected to the other focus. So if we were to have an elliptical shaped room that was surrounded by mirrors on the outside, if we have a light at one of these points, at one of these foci, and the light rays are sent in any direction, they will bounce off the outside and get reflected to the other focus. And the same thing is true with sound waves, and this is actually a big application that we're going to look at. There is a roughly elliptical shaped room in the U.S. Capitol building called Statuary Hall. And this is going to be the subject of our first application problem. Inside the U.S. Capitol building in Washington, D.C., there's an elliptical shaped room called Statuary Hall. It is said that John Quincy Adams put his desk at one of the foci in the room so that he could hear other politicians whispering to each other near the other focus. If the room is 97 feet long along its major axis and 45 feet wide along its minor axis, find the distance between the foci rounded to the nearest foot. Let's go ahead and make a quick sketch of this room. We know it is elliptical in shape. We know that it is 96 feet long along the major axis and 46 feet wide. So remember, the equation of an ellipse is given by x squared over a squared plus y squared over b squared equals 1, where a is half the distance along the major axis and b is half the distance along the minor axis. So in this case, we'll have x squared over, now remember the major axis is 97 feet long, and so the value of a is going to be half that, which is 48.5. So this will be x squared over 48.5 squared plus y squared over b squared. Now b is half of the minor axis. If the minor axis is 46 feet long, then that's going to be 23 feet squared. And that equals 1. Now, what we are looking for, though, is we're looking to see where these two foci are, and we want the distance between them, and we know that the distance from the center to one of them is c. So we're actually looking for 2c, and the relationship that we can use to find c is that c squared equals a squared minus b squared. Now, a is 48.5, and 48.5 squared is 2,352.25, minus b squared. B is 23, and 23 squared is 529. And when we do the subtraction, we get 1,823.25. This is the value of c squared. To find the value of c, we take the square root of this, and we get approximately 42.7. But what we wanted is we want to know 2c, because this is the distance c, and the total distance between them is twice that much. So if we double this, we get the distance that we're looking for, 2c, which is approximately 85.4, and this is measured in feet. And so the distance that we're asked for between the foci is, and we're rounding to the nearest foot, so it's about 85 feet. Now, just really quickly, why was he able to hear the other people whispering? Well, because it's an elliptical-shaped room, if his desk is at one of the foci, and there are people whispering at the other one, even though they're speaking very, very quietly, their sound waves are going to emanate out throughout the room, and they're going to bounce off all of the walls and the ceiling, and they'll all be reflected to where John Quincy Adams's desk is. So he should be able to hear all of the people whispering so long as they're at the other focus. If they're whispering somewhere else, not all of those sound waves are going to be reflected back. Some of them are going to be reflected in different places. But the way that an ellipse works, as far as the reflection properties go, is that any light or sound waves that are sent from one of the foci end up getting reflected precisely to the other. So elliptical-shaped rooms are great for eavesdropping on other people, so long as you're located at one of the foci and they're located at the other.